Hola Ascension Nerds, welcome back to Fluid Mechanics. That's right, we're doing the manometer problem. If you want to start the problem by yourself, please note that I did change this height to 2 meters, which is this, not the overall thing. And for me, these were a little bit more confusing than I would expect. But this time, I'm going to break it down, and I'm going to give you guys some tips that I wish were a little bit more clear to me when I was taking these classes, such as in chemical process analysis, and I already reviewed this, so do check out my playlist for chemical process analysis if you haven't already done so. Or if you're like an environmental engineer, you need a refresher on some of your chemical engineering fundamentals, that's great too. So in this manometer problem, it's very typical for midterm exam. So consider this like an example for your homework, and you might see this on your midterm. So we have a manometer, which is just a U tube, just like what you're watching right now. So in this case, we have water coming down into the U tube, and then in here we have a tank with a gas. So here's some gas with some gravity, with some specific gravity. Density is going to be 1.6 kilograms per meter cubed. And the question is to calculate knowing these heights, we need to calculate the pressure inside the tank, okay? So there's some gas inside this tank, and we just want the gauge pressure. And so gauge pressure is simply what the gauge is reading, neglecting the atmospheric pressure. So the absolute pressure, the true pressure inside the system is going to be adding the gauge pressure plus the atmospheric pressure. But a gauge doesn't really care about atmospheric pressure because it's going to feel atmospheric pressure anyway. So this equation is going to be the absolute pressure, the real pressure in the system, is going to be the gauge pressure, which is what we're trying to solve for, plus the atmospheric pressure. Namely, whatever we calculate, we don't need to take into consideration the atmospheric pressure. If it did say calculate the absolute pressure, then yes, we would take into consideration the atmospheric pressure. So the pressure inside a gauge that is open to the environment, namely if you put a gauge right here, this is open system, and the gauge over here is going to be 0, right? Because it doesn't care about the atmospheric pressure. But the absolute pressure is going to be 1 atm. Okay, so that was the first confusing thing for me during chemical process analysis. Now another thing, last time, when we used the hydrostatic equation, namely this guy, we integrated from the bottom to the top because it's intuitive to think of the hydrostatic pressure as a function of height, PATM plus rho GH. Now you can use this if you want, but in this case, we're going to try a different method because these manometer problems, I'm going to give you a little trick, okay? But what you have to do, you're not going to like this. You're going to like the trick, but you're not going to like what I'm about to say, which is I'm not going to do the algebra for you. So I'll give you the final answer, but you have to get the algebra yourself. So now I'm making sure that you guys are actually practicing. So what we're going to do is we're going to rederive using the hydrostatic equation. Okay, we're going to rederive. So what do we do here? We got to pick some points. So I'm thinking that we can start by selecting this pressure down here. And I'm going to call this point A, because we know the pressure at that point. And I'm going to call this pressure B. Remember, it doesn't matter if it's here or here. Why? Because when we were deriving the hydrostatic equation, remember I told you that horizontally the pressures cancel out. So the pressure down here on the right side is equal to the pressure over here on the left side. And then this pressure over here is going to be pressure C, and this pressure is going to be what we're solving for, which is going to be the pressure of the tank, D. Now, one little trick is that notice how the density of the gas is almost 1,000 times smaller than the density of water, because the density of water is 1,000 kilograms per meter cubed. Honestly, we can neglect this pressure, but we're not going to, so we can practice this. So, I'm going to start by calling, like I said before, we called this point 1 and point 2, but since we already know A, I'm going to call this point 1, and I'm going to call this point 2. So now we can write the hydrostatic equation one more time, dP, and I'm going to move over the dz on the other side, dz, and integrate from the pressure at 1, pressure at 2, dP. Like I said, you can use the other equation that we derived before, but this is going to be a little trick to make this a little bit more intuitive. Z1, Z2, dz, right? Hope you're following here. So now, whoops, this is a P2. So now we have P2 minus P1 is equal to negative rho G Z2 minus Z1. And look, we already have P1, so we're trying to solve for the pressure here, which is really pressure B. So P2 is going to be pressure B, it's going to be pressure B plus P1 minus rho G Z2 minus Z1. If you use this method by saying the pressure that you already know as 1, and you set the pressure that you want to solve for as 2, you can use this equation. We have the unknown is equal to the known minus rho G times your difference in height. The only slightly weird thing is that this may be negative if you're going down, and it will be positive if you're going up. But don't memorize that. I want you to apply the equation that we already derived and use that to your advantage. Okay, great. So now we can start to plug some stuff in. So, well, we don't know Z2, do we? Well, we kind of do. If we can set this as the bottom, as Z2 equals 0. That's the bottom. And we know this height. Excuse me. Okay, so back to the other video. So now that we set this bottom as Z2 equals 0, then this Z1, so we can write that down, Z2 is going to be 0, and Z1 is going to be 3 meters. We can calculate PB to be, well, P1, like I said, is atmospheric pressure. But remember, we're only caring about the gauge pressure. So that's going to be negligible. It's going to be negative times the the density of water times the gravitational constant, 9.8 meters per second squared, times 0 minus 3 meters. Okay, so you can calculate that for PB. Does that make sense? So now we can erase this as 2 and this as 1. So our new 2 is going to be our new 1. And the next pressure we can solve for is this pressure over here. So now we're solving for this pressure. Okay? So now this is going to be PC. PC is going to be equal to PB, which we already solved for here, right? Minus rho G Z2 minus Z1. Well, Z1 is 0 this time, and Z2 is going to be 0.5 meters. All right? And plugging this guy in, we're going to see that PC is equal to PB, which we already solved for, minus, again, the same variables. Minus 1,000 kilograms per meter cubed. It's really hard to tell whether I'm slanting or not. Meters per second squared. Times 0 minus, 0.5 minus 0. 0.5 minus 0 minus 0. So that's going to be our PC. And finally, PD. So we're going to erase this 1, and we're going to erase this 2. So now this is our new 1, and this is our new 2. So our PD is going to be equal to our PC. Don't buy a Mac. Minus, careful with this density. So this is actually going to be the density of the gas, right? Times G. And this is going to be our new Z2 and Z1. Z2 minus Z1. Where, can y'all still see that? Right over here, just in case. Where our Z2 is going to be 1 meter. Z2 is going to be 1 meter. And our Z1 is going to be 0.5 meters. Okay? So, plugging these guys in, this equation is going to be PD is going to be equal to PC, which we solve for here, minus, this is 1.6 kilograms per meter cubed. Kilograms per meter cubed. Kilograms per meter cubed. Times the gravitational constant, 9.8 meters per second squared, times 1 minus 0.5 meters. Alright? And if you plug all that stuff in, you will get an answer of 0.2417 atmospheres, or 2.45 times 10 to the 4 pascals. Now, one little trick that I want you to note is that we can solve for all of this in terms of just the variables and the heights, right? So we have PB over here. You have, let's do it over here. PB, the pressure at B is going to be pressure at 1, which is going to be megajoule, right? It's going to be negative rho G times negative 3, right? PC is going to be the pressure at B, which is right there, and right here, minus rho G times 0.5, and PD is going to be P, so this is going to be the rho of the water, PC minus 1.6, it's going to be rho of the fluid, which is all in terms of the variable, rho of the gas times G times 1 minus 0.5, which is 0.5. And now if I plug in PC into that guy, PD is equal to PB minus rho of the water, G, 0.5, minus rho of the gas, G, 0.5. And then I can plug PD into that guy. PD is going to be rho of the water times G times negative 3. That's PB minus rho of the water times G times 0.5 minus rho of the gas times G times 0.5. This should also be our answer. Quick note on a little typo. I forgot to add a negative right here because of this negative. Okay, now let's try Matlab. Alright, so now we're in Matlab. We're going to try to solve this manometer problem using some clever tricks. So I'm going to start by defining the variables for rho of the water. It's going to be 1,000 kilograms per meter cubed. I'm going to start by saying the rho of the gas is going to be 1.6 kilograms per meter cubed. And then gravitational constant is going to be 9.8 meters per second squared. And what else we have? I think we're good to begin. So we can start by defining the pressure at B. Pressure at B, we said, was going to be negative rho times G times Z2 minus Z1. So we have rho and G, but here we said that Z2 was going to be 0, and we said that Z1 was going to be 3. So we can run this. It's going to be rho of the water. Don't forget that. We can run this, see how that goes. Great, so we have PB. Alright. And then honestly, it's kind of like cheating, honestly. Just copy that and then change these. So now we're going to have PC is equal to PB minus rho GZ2 minus Z1. Where Z2 here we said was going to be 0.5, and Z1 was going to be 0. So now we should have that guy as well. We can run that. And now we have PC. And then lastly, we can copy and paste this again. This is going to be PD is equal to PC. Change the density to that of the gas. And Z2 we said was 1 meter, and this was 0.5. So now PD, and this is going to be in Newton per meter squared, or pascals. And then if we divide this by 101.325, this is going to be in atmospheres. Run this, see what we get. Great, that is in fact what we said. And as a final check, we can see if our equation that we derived was correct, where we said that PD is equal to rho of the water times G times negative 3 minus rho of the water times G times 0.5 minus rho of water, rho of the gas, rather, times G times 0.5. And here's me adding the negative that I just forgot, and the answer is in fact the same.